So this is an interesting Leetcode problem, one that I really like, not because it's complex as a solution, but rather it's about thinking counterintuitively. So let me first set up the problem. What you're looking at is a transit map of bus routes where BR1 is bus route 1, BR2, 3 and 4 and so on. What you're looking at is bus stops in each of these bus routes and how there are intersections between them. The problem, if you look at Leetcode, it's going to give you a list of bus routes with bus stop numbers, but effectively, visually speaking, this is what it's giving you. And the question asks you, given a source and a target bus stop number, for example, something like this and this, they want you to figure out what is the minimum number of bus changes you'll have to do to get from source to target. And this is something as humans we do all the time in the cities. When we commute to work, when we go out, we're optimizing for this specific thing where we're optimizing for the number of bus changes or the number of mode changes, for example, bus plus a train. So the question mentions that there can be about 500 different bus routes and there can be close to 10,000 stops in each. So this is obviously a large city if you want to think about it. So even if you draw a map out, it might be quite confusing to even see where the source and the target are. So in a way, we'll have to think about this not just intuitively, but in a deterministic way, which is where the problem gets interesting. So let's think about the end condition. I always like to think about what do we want to achieve and then backtrack from there to think about specific methods. So ideally, we want to be searching within these bus routes and bus stops. We are not even sure if we can go from source to target. It's quite possible that there is no way to go from source to target. That's another important factor to consider, because this is not necessarily a city where every stop is connected to every other stop. So we may not even have a route from the source to the target. So we are going to have to search, starting from the source, to figure out if there is even a way to get to the target. Ideally, if we design this solution well, then we want to make sure that as we search, at some point we're going to reach the target, and when we do, we also want to have the answer with us at that point, which is the minimum number of bus stops or the minimum number of bus changes to get to that point. So a good solution would be doing the search, and the first time we reach the target, we have the answer already. So when I say all this, you might already be thinking, okay, this seems like a BFS, right? I mean, this is exactly what a BFS guarantees. It tells us that as long as we start from the source and we have a way to get to the target, the first time we get to the target gives us the shortest way to get there. And it's important to think about BFS not in isolation, but also on what kind of graph it's doing this. So each of these nodes, there's a bus stop. So if you did BFS here, the first time you reach the target is actually not the minimum number of bus changes. Rather, it's the minimum number of bus stops separating the source and the target. That changes everything, because that's a different optimization entirely. So what we really want to optimize for is not on a graph of bus stops, but rather a graph of bus routes, because we want to minimize the number of routes that we encounter, because each route is a bus, so we want to minimize that number. So what does that look like in a graph? So graphs are nodes and vertices. So we just already mentioned that because it's a BFS and we want to make sure we minimize the number of bus changes, the nodes have to be bus routes themselves, meaning each node is an entire bus route. So then what does it mean for two bus routes to be connected or not to be connected? And that might be obvious to you now as I say it this way. It's simply exactly that. Two routes are connected if they have a bus stop in common, at least one in common. So for example, in this case, bus route 1 and 2 are connected because they have this particular stop in common, and 2 and 4 are connected because they have this in common, and 4 and 3 are connected too, and 3 and 1 are connected. That's all that's changed from the initial framing here to here. And now we are ready to think about our solution approach, which is going to be a BFS. We are gonna start at a bus route, but here it gets tricky. Which bus route do we start from? We know that we're supposed to start at a particular source bus stop, which in this case is here, and obviously it's only in bus route 2, so we can only start at bus route 2 in this case. So this is our source node, and in this case the target node is in the bus route 3, so again there is just one target node, and all we're really doing is finding the minimum distance in this graph between bus route 2 and bus route 3, and that's a BFS. The first time you start from here and you reach this, the very first time you reach bus route 3, the number of hops you take is the number of bus route changes you'll have to do. But let's think about a different situation. Let's think about a case where the stops are the same, the bus routes are the same, but the source and target, let's change it up. Let's say this is my source. This is where I want to start from as a bus stop, and I want to get to this stop. The source bus stop is in both bus route 1 and bus route 2. Either of them can be our source node, and the target is both bus route 3 and bus route 4. Now a BFS actually involves multiple start points and multiple end points, and that's okay. BFS can handle that. So all we're really doing is we're queuing up multiple start points with the initial distance being set to 1, because if you're going to use at least one bus, then that's one bus, right? So the problem asks you to figure out how many buses do you need to take. So initially you have a distance of minimum of 1. So then you're going to queue things up into your BFS queue, and as you pop things off from the BFS queue, you're going to look at the neighbors and add a distance of 1, or a bus change in this case. And the first time you reach any of these target nodes, now we have multiple target nodes, at any point you might reach one faster than the other, and if you do, that is the answer. That's the minimum number of bus changes, or the minimum number of buses you'll have to take.